Hello everyone, today I'm here to talk about the paper, the impact of the size of the partition in the performance of Bath algorithm. So in this presentation I will start by introducing the motivation, followed by a quick look at the Bath algorithm before moving on to the parameterization, implementation and analysis of the results. Finally, I will talk about the statistical analysis performed, ending with the paper's conclusions. So starting with the motivation. As you know, in the last decades, metristics have played a key role in solving complex problems, which led to a significant increase in the number of metristics. However, due to this rapid growth, careful analysis and understanding of the best parameter values has been underestimated, affecting the true possible performance that these algorithms can have. Following from the paper Bath Algorithm for Discrete Optimization Problems, an analysis, this paper intends to analyze the possibility of the existence of one more parameter in the discrete version of Bath algorithm. To do this work, we start by doing a literature analysis, followed by a discrete Bath algorithm implementation using a scheduling problem with auxiliary of Visual Basic in Excel, followed by statistical analysis and ending with the conclusions. Moving on to the discrete Bath algorithm. Bath algorithm is a population metristic based in swarm intelligence, which was developed by Dr. Xin-Shi Yang in 2010. However, this metristic was not developed for discrete problems, and therefore it was necessary to find a discrete approach so that it could be used in such problems. So in terms of the algorithm, we start by initializing a random population of bats. Next, a value is generated between fmin and fmax that will represent the size of the partitions, which will be internally sorted in descending order of processing. Next, there are swap and insert operations between partitions, depending on the random value obtained. In the next phase, a part of the best solution is placed in each of the solutions of the population, and there is an adjustment to make them feasible. Finally, a set of operations are performed on the best solution so far in order to try to improve it. This process is repeated n times until the stopping criterion is reached. So as we can see, much of the algorithm involves fixed processes and well-defined parameters. However, during the perform loudness operation phase, the literature only says that the partition value should be equal to or less than 50% of the solution size. However, nowhere does it explain why this value is necessary, and this question, raised in a review of a previous paper, was the basis for this work. Having the algorithms implemented, it became important to understand the best parameters for the problem at hand. For these, several combinations were tested, considering the values found in the literature. This range of values can be seen in this table 1. Note that for each combination 5 iterations were performed for a total of 100 iterations. In the results analysis, two essential criteria were used: lowest average of the 5 values for a given parameter combination and iteration with the lowest minimum. Thus, for discrete path algorithm, the best parameters were fmin equals to 4, fmax equals to 8, 10 bats, and a stopping criterion of 500. With the results obtained in the parameterization, the next step was to apply the discrete path algorithm to the normally distributed, randomly generated instances. Initially, the results of 30 instances with 5 machines and 150 jobs, which was the dimension used during the parameterization, were analyzed for a maximum partition size of 25, 50, 75, and 100% of the size of the problem. The average deviation relative to the best solution obtained for each instance can be seen in Fig 1, where the blue color line represents a maximum partition size of 25% of the number of tasks, the orange color 50%, and the gray and yellow colors the 75 and 100% respectively. With the analysis of the values obtained in each instance, and supported by the graph presented in Fig 1, there is no clear trend and it is possible to observe a maximum value of the partition size, which results in a better performance than the others. Following this process, Doubt arose about the impact that the size of the instance would have on the results was raised, and, as such, the analysis was extended to problems half and double the size, I mean with 75 and 300 tasks respectively. This study was carried on, and the average relative deviation from best solution obtained for each maximum partition size can be seen in Table 2. Given the values in the table, it is possible to see that by decreasing or increasing the number of tasks, the performance differences between the maximum partition size remain close. It is only interesting to point out that in the three cases, the size that had comparatively the worst results was the one that is considering the value for the original algorithm, that is, 50%. However, although this analysis is possible from the point of view of the observed values, it in no way proves their superiority or inferiority to the others. Thus, it becomes necessary to use statistical analysis tools to try to mathematically prove the difference between the hypotheses tested. To do this, it was used the one-way ANOVA to analyze the means of multiple populations, in this case, the results for different problem sizes. In fact, this statistical analysis serves as mathematical proof for what had been pointed out in the results, that is, the non-superiority of performance of a maximum partition size over the others, since the p-value is not significant in any dimension study. In fact, this analysis led to the conclusion that there is no value for the maximum size of the partitions that achieves better results than the others, that is, that this should be also considered a parameter, adding a new variable to the discrete path algorithm. So, in terms of future work, a more careful analysis of each meteoristic and its current parameters should be done, because can lead to a better understanding of each algorithm and its parameters, serving for the evolution and improvement of the algorithms themselves. Also, the hybrid models will tend to evolve as the result, because the algorithms that are joined will be supposedly better. This also led to new possibilities within the path algorithm, which can be explored considering this new parameter. Thank you all for the attention. If there is any doubt that was left, please write me an email and I will try to answer the best way I can. Thank you.